Hi, good day, everyone, and welcome to the first lecture we have in the year 2023. So, Happy New Year, everyone, and I hope that you're going to enjoy this session however online. And if you're going to notice that this week I brought the lecture from the week number 11 this week because mainly we are going to have an assignment number 3 is going to be based on the material that we're going to cover in this slide. So the lecture topic is going to be about the bulk deformation processes. Now, the bulk deformation processes are any process that we're going to use the force to overcome what we know it as the uh, shear stress uh, to make a permanent deformation in the material. So the content we are going to have for this slide is going to be the stress strain properties of the materials, the different bulk deformation processes, and we are going to focus on the three main processes, which are going to be the forging, the extrusion, the rolling. And also again to go over the process of the wire and the bar drawing operations. Now when I say I'm going to focus on the three main processes, which are the forging, extrusion, and the rolling, because these are going to be the part that we're going to have a calculation for these processes. So first we need to know what are the mechanical properties in the design and manufacturing. The mechanical properties will determine the material behavior when they're going to be subjected to mechanical stresses. The properties will include the elastic modulus, the ductility, the hardness, and other various measures of the strength. The mechanical properties important to the designer, such as the high strength, would usually get to make the manufacture more difficult. Now just let me give you an example about you're going to have a rod made of the copper and another one with the same dimension, I mean the diameter, which is going to be made of steel. So definitely if you're going to try to bend the one which is made of the copper, is going to be much easier using less forces to be bent, while it's going to be much harder if you're going to do it with the same bar that's made of the steel. So first we need to know what are the static stresses we have in general. So we have the tensile stress, which tend to stretch the material. So just remember the same bar we get again as an example and try to pull it from both sides to make it longer. So it's going to be stretched. So this is what we call the tensile stress. Now the other type we have is compressive. And this one is tend to squeeze it. So we're going to push the rod from both ends onward. This will be a compressive. And also we have the shear that tend to cause the adjacent portions of the materials to slide against each other. And that's what's happening when you try to cut it using a sharp edge. And I think that we explained the shear stress when we talked about the uh, cutting processes on the orthogonal model. The stress strain curve will show the basic relationship describing the mechanical properties for all the types. So once again, here we have the tensile, we have the compression, and we have the torsion. One of the best way to check the properties of the materials is what we know as the tensile test. The tensile test is the most common test for studying the stress-strain relationship, especially in the metals. And I say especially in metals because actually it can be done also with different materials. We can do it even for the plastic, for example. We can do it with even the ceramic to a certain level, but usually it can be done with any material that can be used for testing. And the machine we can see on this photo is describing the parts that we have for the tensile test machine. As you can see here that we have the we have the two parts. One of them is going to be the moving parts or the moving cross head, and we have the fixed cross head. The specimen, which is going to have the two gauge marks, with the specified length is going to be fixed between these two crosshead. So as we're going to apply the force, the moving crosshead is going to be moving down, and this will cause the elongation of the specimen. So it's going to reach the new length. And of course, because the volume is constant, you will see that the cross-section area is going to be dropped down. And thus, in all the cases, as you know, that the volume of the cylinder is equal to the area of the base multiplied by the height. So as long as the height is going to be longer, the cross-section area should be get smaller. So the typical progress of the tensile test for the ductile material will be shown in this diagram. So you can see that at the beginning we're going to have the original length, and as we're going to be applying the force, the length is going to be extended until we're going to reach the necking stage. And this necking stage is going to be appeared at the point where the reduction in the cross-section area is going to happen rapidly until the fracture will be happen. And then we're going to put the two parts together to have the final length of the specimen after the extension has been happened. So the engineering stress and strain can be given with the following equation. The stress is going to be equal to the force that magnitude we applied divided by the original cross-section area. And the strain is going to be equal to the difference in the lengthen, the final length minus, or the instantaneous length minus the original length divided by the original length. And this value is going to be unitless because you know that the length R is going to be in meter minus meter divided by meter, and thus we are going to have unitless. While in the case of the stress, we are going to have the force, which is in Newton, divided by the area, which is in meter square, and thus we are going to have the unit of Pascal for this operation. The result of the tensile test can be described in the stress-strain plot. So in the typical stress-strain plot, we are going to have two regions indicate the two discounts from of the behaviors. First one is what we know as the elastic region, and the other one is going to be the plastic region. So the turning point between the elastic region and the plastic region is going to be what known as yield strength at that point. So what's happening in the elastic region? So the elastic region is going to be a prayer of the yielding of the material. So before that, we're going to follow what we know as the Hooke's law. And during the Hooke's law, we're going to have the material is going to have an elasticity. That's mean any deformation we're going to have in that case is going to be simply relieved as we remove the force. After we're going to reach the yield strength, we're going to enter the plastic region. So after the yielding of the materials, any deformation is going to be permanent. Again, in the elastic region stress strain curve, what we're going to have that the relationship between the stress strain are going to be linear. And the material will return to its original length when the stress is going to be removed. The process is going to follow what we know as the Hooke's law. We say again that stress is going to be equal to the modulus of elasticity, or what we know as the Young modulus, multiplied by the strain of the material. The E is a measure of the inherent stiffness of the material. So harder materials, more stiffness material is going to have higher value for the E. Its value is different for different materials. For example, again, to take the steel is going to be higher than the aluminum, and the aluminum is higher than the copper, and so on. So the modulus of elasticity, or the Young modulus for different materials, can be shown in this table. So as you can see here, then the aluminum, for example, is going to have 69,000 megapascal, while if we're going to go, for example, for the alumina, it's going to have 345,000 megapascal. Diamond, which is the hardest material, is going to have the value of 1,035 thousandths, or which something like 1,035,000 megapascal. Other materials like the titanium, the tungsten, we have also, for example, the iron, and we do have the tungsten carbide, which is one of the famous cutting tool, is going to have 552,000 megapascal for the models of elasticity. The yield point in the stress strain curve, as we mentioned earlier, is going to be the turning point between the elastic region and the plastic region. So as stress is going to be increases, a point in the linear relationship is going to be finally reached when the materials begins to yield. The yield point y here, the stress at this value and that strain, can be identified by the change of the slope at the upper end of the linear region. The y is strength property, and other names of the yield point can be the yield strength, yield stress, and also the elastic limits. After the yield point, the material will start to behave as plastic material. So we are going to enter the plastic region in the stress strain curve. The yield point marks the beginning of the plastic deformation, and the stress strain relationship is going to be no longer guided by the Hooke's law. As the load is going to be increased beyond the y value, the elongation proceeds at a much faster rate than before, and this will cause the slopes of the curves to be changed dramatically. The tensile strength in the stress strain curve, or what we know it here as the top or the maximum load, is the elongation usually going to be accompanied by the uniform reduction in the cross-sectional area, as we mentioned earlier. And this will be consistent with the maintaining of the constant volume. So just remember that whenever you're going to change the length, the volume is going to remain the same, and this will be only happen if the cross-sectional area of the specimen is going to be dropped. So finally, as we are going to apply the load F, we'll reach the maximum value here, and the engineering stress at this point is going to be called the tensile strength, or the TS, or what we call also as the ultimate tensile strength of the material. And this can be given as the value of the maximum load, now not the initial load we had, divided by the original cross-sectional area of the specimen. The tensile strength and tensile strength for the selected materials can be given in this table. So once again, you can see that, for example, for the aluminium, the value is going to be 28 megapascal for the yield, while it's going to be 69 material for the tensile strength. If I'm going to go for the, let's say, the copper, you can see that the value for the yield strength is going to be 70 megapascal, while the tensile is going to be 205. So once again, just remember that this column would represent the maximum stress that the material can be taken before it's going to have the fast degradation in the cross-sectional area. The steel 175 by 300, the stainless steel 275 by 650, and we have the titanium alloy is going to have 800 by 900. The ductility of the materials and how this will be changed actually, and how this will affect the tensile test operation. So the ductility is the ability of the materials to plastically strain without fracture. Now let's have an example about this wood. If I get to have a piece of wood and I get to have a piece of aluminium and a piece of steel, so definitely if I get to try to deform or try to bend the wooden one, is going to be break before it's going to have actually plastic deform, unless if of course you're going to add some heat. So that's mean that the wood is non-ductile material. The same thing if I get to have this ceramic. The same thing if I get to have, for example, a plastic material, okay, which is going to have non-plasticity. While in the case of the other ductile material, is going to be bended without having a fast fracture during the bending operation. The ductility measurement is going to be the elongation or the area reduction value. So the elongation is going to be simply the delta L divided by the original length. So the final length minus the original length divided by the original length, or it's going to be the original cross-section area minus the final reduction, final cross-section area divided by the original cross-sectional area. So EL is the elongation, LF is specimen length at the fracture, LO is original specimen length, and the LF is measured as the distance between the gauge marks after the two pieces of the specimen are going to be put back together after the fracture. The AR is the area reduction, and the AO is the original area of the test specimen, and the AR is the area of the point fracture. So the ductility as a percentage of the elongation for the selected material is given in this table. So you can see once again that, for example, for the aluminum, we're going to have 40%. Now let's go for a non-ductile material or less ductile material, and let's take a look for the ceramic. It's 0. For the polymers, if we're going to have the thermoplastic polymers, the elongation value is going to be 100%. The thermosetting polymers, which is going to be a little bit harder, that's going to have only 1%. And for the elastomers, it's going to have 1%. So among these values, that means that the elastomers and thermosetting is going to have less ductility. That means actually when you're going to change that, it's going to return back to the original shape because simply they don't have any plasticity. They are not going to have a deformation by adding the force. While for the other materials, you're going to have a reasonable value. Steel 30%, steel alloy is going to have 20%. We have the steel or stainless steel or the austenitic steel is going to have 55%. And what else? We have for the aluminum alloys with heat treatment is going to have 8%. For the annealed aluminum, we said it's going to be 40%. For the copper, anneal is going to have 45%. Now, the cast iron is not ductile material. I mean, we cannot make a deformation for it because it's going to be break. Actually, in the cold work, and that's what we're going to explain later. Now, whenever we had earlier, we know it as the actual stress strain, but we have the true stress and true strain. So the true stress is the value obtained by dividing the applied load by the instantaneous area instead of the original area. So the stress here, the true stress, is going to be equal to the force, the instantaneous force we're adding, divided by the actual or the instantaneous area resisting the load. True strain is more realistic assessment of the instantaneous elongation per unit length. So the strain here, the true strain, is going to be the natural logarithm of the length, the instantaneous length, divided by the original length. So if I get to redraw the stress strain curve versus true stress strain curve, you will see that the difference between them is that actually the fracture is going to be happen after we're going to have the fast degradation in the cross-sectional area, and this will cause stress will be dropped dramatically after the value of the TS. And in the case of the true strain diagram, you can see actually that things is going to be less dramatically dropped, and the value doesn't have to be exactly like the yield point stress as we can see in this diagram. So the strain hardening or the work hardening in the stress strain curve, what we're going to have here, wait a second. So we know that the true stress increases continuously in the plastic region until we're going to have the nicking. In the engineering stress strain curve, the significance of this was lost because the stress was based on an incorrect area value. It means that the metal is becoming stronger as strain is going to be increases. So I think this will give you a simple hint. The strain hardening. The material will become stronger as the strain is going to be increasing. So actually, if I again to roll a material or again to compress a material, is going to be stronger because its length has been changed. Because we added the forces, we changed the metal strain, and thus the material is going to be stronger. So the true stress strain in the log plot can be defined as a linear line instead of curve. And this linear line is going to have the value for a slope. So you can see that the slope value n is going to be equal to the a divided by the b. So we're looking for the tangent of this angle. So we can see that we have a k value at the projectile of this line, and we have the k value is going to be when the true strain is going to be equal to 100%. So let's see how we are going to use that. Because of it's going to be a straight line in the log-log plot, the relationship between the true stress and the true strain in the plastic region is going to be called the flow curve. And S is going to be the YF, which is called the flow stress. So the value of the stress we are going to have here is going to be the flow stress, which can be found from the following equation. The flow stress is going to be equal to the K, which is strength coefficient, this value here in megapascal, and multiplied by the strain at any point up to the power n, which is strain hardening exponent, which is the slope of that straight line. So the categories of the stress-strain relationship is that first we're going to consider that the material is going to be perfectly elastic. Second, that elastic and perfectly plastic, or we're going to have elastic and the strain hardening. So perfectly plastic, that means it's going to be straight force. We're going to have this line going to be horizontal. Whenever we're going to add the force, the material is going to be simply deformed. We have the elastic and then perfectly plastic. That's when we're going to have the force to be increased, the stress going to be increased until we're going to reach the yield point, and then after that we're going to have a horizontal line for the plasticity of the materials. And also we have the elastic and the strain hardening, and that's what we have in most of the cases in the case of the forging processes. So perfectly plastic, whenever we're going to have the stress, this strain will be changed linearly. Now in that case, we're not going to have any plastic deformation. And that's what we have in the case of the brittle materials. So once again, we go back to the example of the wooden piece. So when we try to bend it, it's going to increase the stress. But when you relieve the stress, the length of the material will, the shape of the material will come back to the same positions. We have the second case when we're going to have the elastic and perfectly plastic. In that case, the K value is going to be equal to the yield strength. And the slope of the line in the plastic region is going to have 0n. That means simply we're going to have that the value for the flow stress is going to be equal to the K value directly. And that's what's happening with the metal when it's going to be heated to a high temperature. So when you heat the materials to a high temperature, it's going to get softer, and thus the same force is going to, the same pressure or the same strength is going to be applied in order to make the deformation. We have also the elastic and the strain hardening, and in that case, the K value is going to be more than the yield strength value, and the N value is not going to be equal to 0. So we're going to have an actual slope for this curve. And that's what's happening in most of the ductile materials when they're going to be cold work. So every time we're going to compress the materials or going to stretch the materials, the K value is going to be higher than the yield strength. We need more stress in order to make the change in the shape of the metal. Now, another useful test to test the properties of the materials is going to be the compression test. So this one is opposite to the case of the tensile. In the tensile, we stress. In the case of the compression, we compress. Okay. So what's happening here, as you can see in the machine, that we're going to apply the load that squeeze the ends of the cylindrical specimen between the two platens. So these are the two platens, one to the table and the moving crosshead. We put the specimen in between. We're going to squeeze it. In that case, the length is going to be dropped, or that what we call the height. The height is going to be dropped. So once again, the volume is constant. That means every time we're going to drop the length, the diameter or the cross-sectional area is going to be increased because the volume once again is constant. So in that case, you can see that the stress value is going to be equal to the F over A, but it's going to be negative because we are compressing, no stretching. And the elongation or the strain is going to be equal to the H minus the HO divided by the HO, as long as the H is going to be less than the value for the HO, we are going to get this value as negative. But we always going to get this value as in absolute value or a positive value for the convenience of the calculations. Now, for the stress strain curve in compression case, you can see that instead of we're going to have the TS value, then we're going to have the sudden or the dramatic drop in the cross-sectional area, and then we get the fracture. We can see that the pressure is going to keep increase, stress will keep increase because uh, logically that the material is not going to be broken. It's always going to be compressed, but it's not going to be bended between the two parts of the machine. So the shape of the plastic region is going to be different from the tensile test because of the cross-section. Simply going to keep increasing to infinity. Calculated value of the engineering stress is going to be always high. Now, the tensile test with the compression test. What will be the difference between them? Although the differences will exist between the engineering stress strain curves in the tension and the compression test, the true stress strain relationship are going to be nearly identical. So since the tensile test results are going to be more common, the flow curve value for the K and the N from the tensile test data can be applied to a compression test. When using the tensile K and N value data for the compression, we need to ignore the nicking, which is going to be a phenomena which is going to be peculiar to straining induced by the tensile stresses. Now, all these properties are going to be applied in what we know as the bulk deformation processes. Here we are going to cover the most common deformation processes. So the metal forming operations, which causes the significant shape changes, is going to cause a large strain simply by deforming the metals parts whose an initial form is going to be bulk rather than a sheet. Okay, so the bulk deformation is going to be dealing with the bulk materials rather than the sheet. If we're going to work with the sheet, we're going to call it a sheet metal working. So these processes will suppress the metal sufficiently to cause a plastic flow into the desired shape. The starting forms usually going to be a cylindrical bars and pellets, rectangular pellets and slabs, and similar shapes. It can be performed as a cold, warm, and hot working operations. Now, when we are going to say that this operation is going to be cold form or hot form, it's going to depend on the temperature we are going to use. So the cold forming, if the deformation process is going to be happen when the temperature of the specimen or the bar or the bulk or whatever the thing is going to be less than 0.3 of the melting point. So if it's going to be done at room temperature of 25 degree, or we can do it even at, let's say, 100 degree, it's going to be considered to be a cold forming. In that case, we're going to have better accuracy control because there will be no expansion or no contraction in the volume. We are going to have better surface finishing because there will be no oxidization for the metal due to the high temperature. It's going to cause strain hardening. We said that strain hardening is how to get stronger materials because you change the strain of the material. Large forces are going to be required, and this will be a negative point. Clean surfaces, which is good because once again, we're not going to have any
changes in the meteorology properties of the materials. But the problem is that we're going to have some limits on the amount of the deformation, especially for the larger parts. If I get to heat up the metal to a temperature which is going to be more than 50% of the melting point, I can simply call it as a hot forming. Now, by the way, in between, we're going to call it as the warm forming. So, in the case of the hot forming, large shape changes are going to be possible because the material is going to be softer. Or the value of the y is going to be always equal to the value of the k, and this will be constant. Lower forces are going to be required. We're going to prevent the fracture because the material is going to be more ductile. No work hardening. So maybe this sometimes this will be a bad thing because we're going to have some residual stresses inside the material. Accuracy is going to be less because we're going to have expansion and we're going to have contraction after the cooling down. Heating for the forming is going to be greater energy use. And finally, because the high temperature will cause the oxidization of the surface, we're going to result in a poor surface finishing for the finished part. Now, the temperature effect on the manufacturing processes can be explained in this diagram. So we can see that the strength and the ductility against the temperature. The strength and the ductility is going to be higher at lower temperature. So, sorry, tensile strength and these strengths is going to be higher at lower temperature, while the ductility of the material will be simply going to be increasing as the temperature is going to be increased. Now, this will give you a hint why the blacksmith is always going to heat up the metal before it's going to do the work on it. Because simply he's going to increase the ductility of the material. The metal at lower temperature will require higher strength to cause the deformation. When I get to heat up, it's going to get smoother. The four basic bulk deformation processes we have are, we have the forging, which work is going to be squeezed and shaped between the opposing dies. We have the extrusion, where the work is going to be squeezed through a die opening, and thereby is going to take the shape of this opening. We have the rolling, where the slab or the plate is going to be squeezed between the opposing rolls. Finally, we have the wire and the bar drawing, where the diameter of the wire or the bar is going to be reduced by simply pulling it through a die opening. Okay, now you know this example. If I'm going to have the hammer and the anvil, this will be a forging. If I'm going to have two dies are going to be constant moving and squeeze the part, this will be forging. For the extrusion, if I'm going to, for example, put some paste inside this syringe and I'm going to squeeze it by moving this syringe piston inside. So the material is going to be forced to leave through the syringe outlet, which is going to have a cylindrical shape. And thus I'm going to make a cylindrical shape. And that's what they're actually using for the decoration of the cake. Okay, so you can simply put the cream in the applicator and then you can squeeze it, force it to go through the die, and it's going to take the shape of the die. But this case is going to be done in the case of the metal. For the rolling, if I'm going to put the slab or the plate between two rolls, rotating in the opposite direction, sending the material in the one direction, and thus when I say opposite direction, because one of them is going to be clockwise, the other one is going to be counterclockwise. So the force added by these two rolling is going to cause the materials, the slab or the plate to be thinner. It's going to take the distance, it's going to have the same thickness, which is going to be distant between the rollers. And we have the wire and the bar drumming. So in case of pushing the wire and the bar through the die opening, we're going to pull it from the die opening, and thus we're going to force the diameter to be reduced to take the shape or the diameter of the die we are using. So we're going to start with the first and the oldest method among all, which is going to be the forging operation. So in the forging operation, the formation process in which work is going to be compressed between the two dies. It's one of the oldest metal forming operation. It's dated back to about 5000 BC. The products are going to be among the different products going to be the engineering crankshafts, the connecting rods, the gears, the aircraft structural components, the jet engine, and the turbine parts. Also, basic metals industries use the forging to establish the basic shapes of the large parts that are going to be subsequently machined to a fine geometry and sizes. By following this link, you can see some example about the forging processes. The the classifications of the engineering operations or the engineering forging operations. So we have the cold with the hot forging. The hot of the warm forging, the advantage is the reduction in the strength and increases in the ductility of the work metal, as we mentioned earlier. As you increase the temperature, the strength are going to be dropped, while ductility is going to be increasing. In the cold forging, the advantage is increases strength due to strain hardening. That doesn't happen in the case of the hot or the warm forging. Now, of course, you know now the hot forging is going to be when the temperature of the metal is above 50% of the melting temperature, and the cold forging when the temperature is going to be less than 30% of the melting temperature. Now, the other classification of the forging operation is going to be the impact with the press forging. So in the impact forging or the forge hammer is going to be applies an impact force. So we're going to keep hitting. So the die is going to actually leave the part and come to hit it by the impact force. And the other term is going to be the forge press, where it's going to apply a gradual force on the part to make the deformation. The different types of the forging operation are going to be the open die. So you can see that we're going to have two dies open. The parts are going to be included with them. We have the impression die forging. Okay, this is the impression die forging. So we're going to have two dies, but it's going to have this die is going to have cavities. And this one also has something called the flash, so I can talk about it very soon. We have also the flashless forging, and once again, the specimen is going to be contained within the mold, and thus we're going to compress it and force it to take the shape of the cavity of that mold. So in this example, you can see that the open die or the offset forging, we have the specimen, we put it between the two dies, we start to have the impact on it. Once again, this one is adding the impact. We have another tab which can have the gradual forces on it. So a compression of the work part between the two flat dies, similar to the compression test when the work part has a cylindrical cross section and is going to be compressed along its axis. Deformation operation will reduce the height and increases the diameter of the work. And the common names include the upsetting or the upset forging operation. So if I get to analyze the open die forging with the case of no friction, if no friction occurs between the work and the die surface, then the homogeneous deformation is going to be occurs. So that the radial flow is going to be uniform through the work part height, and the true strain is going to be given by the equation that the true strain is going to be equal to natural logarithm of the the original height of the part divided by the instantaneous height of the part. So you can see that with this equation, we can have the initial strain, the mid strain, and the final strain. For the value for the flow stress, it can be calculated by multiplying the K value. As you remember that we have a specific K value for the different materials, and multiply by the true strain F to power n. Now, in real life, we're going to have a friction between the specimen and the die in this point. And this will cause that the metal is not going to be perfectly sliding with the die, even we're going to add some lubricant. So this will cause something called the barreling. Now the barreling happens because the materials here is stick with the die. So in the case of the open die forging with the friction between the work and the die surfaces constrain lateral flow of the work. This will result in the barreling effect. In the hot open die forging, the effect is going to be even worse due to the heat transfer at the die surfaces. And this will cause that the metal is going to be cools and increases its resistance to the deformation. In this case, the forging forces is going to be calculated by the following equation: the Kf multiplied by the flow stress multiplied by the area. So the flow stress has been calculated from the previous equation, which is equal to the K multiplied by the strain out to power n, and the area is going to be the instantaneous area, and the Kf can be calculated with the following equation. The Kf is going to be, or the shape factor is going to be equal to 1 plus 0.4 multiplied by the coefficient of friction, mu, multiplied by the instantaneous diameter, divided by the instantaneous height. That means that the Kf value is going to be different from the case number 1 to the case number 2 to the case number 3. So we need to calculate different value for the Kf. And thus, the forces in the case number 1 is going to be less than the case number 2 and less than the case number 3. Because each time we're going to have strain hardening for the part, and this will resist the material deformation, and this will cause the force required to cause the deformation. So that's what's happened in the case of the open die forging with the friction. You can see that the burn is happening here. The material that has dropped out from the specimen is what we call the skills, and this happened due to the oxidization of the surface due to the high temperature. Now we're going to have the first example for the, wait a second, did I miss something? Anyway, so this will be our first example on the open die forging. So in this example, we're going to have a cylindrical workpiece. It's going to be subjected to a cold offset forging operation. The starting piece is 75 millimeter in height. Okay, now this is the original height, the HO, and 50 millimeter in diameter, that's the DO. It is reduced in an operation to the height of 36 millimeters. So we take it down from 75 to 36. The HO and the H final. The work materials have the flow curve, which is defined by the value of the K equal to 350 megapascal and the N of 0.17. Now, if we're going to assume that the coefficient of friction is equal to 0.1, we need to find the following. First, determine the forces as the process just begun. At the intermediate height of 62 millimeters, at the height of 49 millimeters, and the final height of 36 millimeters. So here we are going to have the HO is given, and we are going to have the H2, the H3, and the H4. And we need to find what will be the value of the forces required at each stage. So as long as we're going to have the K, we have the N, we have the new value, then it's going to be very easy actually to find out what will be the value for the YF, the KF, the value for the force. So if we recall the equations we had, just let me write down these equations here before we're going to go. Okay, so we need to calculate the strain, which is the length of the HO over the H instantaneous. The YF is going to be equal to the K multiplied by the strain up to 4n. Okay, and then we need to find the value for the KF, and this will be equal to 1 plus the 4 multiplied by the mu multiplied by the diameter and divided by the value of the area, I think. I don't remember that very well. We can check this one later. And finally, we can find the value for the force, which is going to be equal to the KF multiplied by the YF multiplied by the instantaneous area. So that's what we need to find. In that case, we are going to find 4 value for the mu, 4 value for the YF, 4 value for the KF, and 4 value for the forces. So the solution of this example, and just remember that you are going to have a question similar to that in your assignment, and we're going to have similar question in the final exam. So let's go for the solution. First, as the process began, the work volume is going to be equal to, now that's the volume of the cylinder. So it's going to be equal to 0.75 pi multiplied by the diameter squared divided by 4. 75 is the original height, and this is the cross-sectional area. The diameter squared divided by 4 multiplied by pi. That's the cross-sectional area. And this is the original height. So the volume is going to be 147,226 and 62 cubic millimeters. Just remember that this volume is always going to be constant. At the moment contact is going to be made between the upper die, the H is going to be 75 millimeters and the force is going to be equal to 0. At the start of the yielding, the H is going to be slightly less than 75 millimeters, and we can assume that the strain is going to be equal to 2 in 1000. Then the flow stress is going to be calculated as following. Now, for the flow stress, the YF, the K is given, the N is given, and the mu is assumed to be 2 in 1000. So simply we're going to substitute the values. So we're going to have the 0.002 up to 4.17 multiplied by the K. 0.002 up to N, power N, and multiplied by the value of the K. And the answer is going to be 121.7 megapascal. Now, the next step, we need to find the value for the diameter. The diameter originally was equal to 50 millimeters, and thus the area is going to be equal to the pi multiplied by the diameter squared divided by 4, and the area is going to be 1963.5 millimeters squares. So we can calculate the value for the KF, and the KF is going to be, oh sorry, this is H not A. The value of the KF is going to be equal to 1 plus 0.4, and I wrote as 4, so it's 0.4 multiplied by the mu multiplied by the diameter divided by the H. Now, the value for the D is the same, the value for the H is the same, 75, and the value of the mu is given, and we have 0.4, so we can put all the parameters in, and we're going to get the value of the KF is equal to 1.027. Now we're going to go to the next step. Now we have the value for the YF, we know the value for the KF, we know the area, and we can calculate the force. So the KF is going to be, the F is going to be equal to the KF multiplied by the YF multiplied by the A. Substitute the value, I'm going to find the value is going to be equal to 245,410 newtons. Now the height is going to be dropped to 62 millimeters, so we need to calculate the new value for the strain. It's going to be the length of the original height, which is 75, divided by the 62. And we're going to get that the new strain is equal to 0.1904. Next, we need to use this strain to calculate the value of the flow stress YF. So we're going to have 350, we're going to have the 0.19 up to 4.17, and we're going to have the new flow stress going to be equal to 264 megapascal. Now, we need to calculate the new diameter. Just remember that the volume is constant, and we have now a new height. So we can find the new area, which is going to be equal to the original volume divided by the new height, and this will be equal to 2,375.2 millimeters square. Now, if I know the area, I can find the diameter by using this equation. The diameter is equal to the 4 multiplied by the area divided by pi under square root. So we substitute the area in this equation, and I will find the diameter. So you can see that diameter has been increased from 50 millimeters originally to 55 millimeters. Now, the KF, we are going to substitute the new diameter, we are going to substitute the new height, and we are going to find the value for the KF. New KF is equal to 1.035. Now I'm going to substitute the KF, the YF, and the new area to find the value for the force, and you can see that the force has been almost multiplied by 2.5 to cause the deformation. Now what's happened is that the material got harder because simply we have what we call the strain hardening of the materials when we change its strain. Now we're going to continue doing the same step for the new two heights. So what's happening at the height of the 49 millimeters, the force will be found to be 955,642 Newton. At the height of 63 millimeters, the force is going to be 1,467,422 Newton. So we're going to keep compressing, and what's happening is that the height is going to be dropping and the force required is going to be higher. Now, other operations that classified as an open die forging or related operation will include the following: the fullering, which is going to be a property or the roughing forging to reduce the cross section for further forging later. We have the edging, which we're going to have a concave dies instead of the flat one. And we have the coding, which is going to be an incremental forging process like that. So we're going to take it step by step until we're going to have the final thickness. Now, in the case of the impression die forging, we said that we're going to have some cavity inside the die. The composition of the work part by the dies would inverse of the desired part shape. The flush is going to be formed by the metal that flows beyond the die cavity into a small gap between the die plates. The flash must be later trimmed, but it's going to be serves as an important function during the compression. First, as the flash is going to be formed, the friction resist continued the metal flow into the gap, and this will constrain the metal to fill the die cavity. In the hot forging, the metal flow is going to be further restricted by the cooling against the die plates. So basically that's what's happened in the operation. You can see the flash is going to be generated, and this will relieve the pressure inside the die cavity, and thus we're going to have less forces to be used. So that's what's happened. We are going to add the forces, going to reach the maximum stress, and then it's going to drop down because the flash has been generated. Now the final type is going to be the flashless forging. As you can see here, we're going to put the work part inside the die cavity, which is going to be totally enclosed, so no flash is going to be generated. And we're going to add the forces, and this will cause that the part take the final shape of the die cavity. So what's happening is the compression of the work in the punch and the die tooling, whose cavity does not allow for the flush. And starting, work volume must be equal to the die cavities volume within a very close tolerances. So the volume of the original part should be equal to the volume of the final part or the cavity of the die volume we are going to have at the end. The process will control more demanding than the impression die forging. The best suited for the part geometries are going to be simple and symmetrical. Otherwise, you're not going to be able to take it out from the die cavity. Often it's going to be classified as the precision forging processes because the final shape is going to be exactly the shape of the part we would like to have. Now for the impact or the drop forging. Is the apply or the impact load against the work part, and this will have two types. First, the gravity drop hammers, where the impact energy from the falling weight of the heavy ram. Or we have the power drop hammers, where they're going to accelerate the ram by pressurize the air or the steam. Disadvantage of the impact or the drop forging is that the impact energy will be transmitted through the anvil into the floor of the building. And this of course going to cause some damage to the base of the building. Commonly used for the impression die forging. So this is the example of the door forging hammer fed by the conveyor and the heating units and the rides of the cells, as you can see. So the material will be started to be fed, the hammer will be taken up, and then it's going to be dropped down to the anvil. The part is going to be between the anvil and the ram, and thus it's going to have the process of the forging to be done. Now, other forging processes will include the forging presses will include the apply of the gradual pressure to accomplish the compression operations. The types are the mechanical press, which convert the rotation of the drive motor into a linear motion of the ram. We have the hydraulic press, where the hydraulic piston is going to be actuates the ram. And we have the screw press, where the screw mechanism will drive the ram. The impression die forging example is going to be the bolt manufacturing. Here you can see that we feed the part. This stop will give us exact length of the parts to be forged. We're going to close the die in the second stage, and then we're going to push or punch the shape to have a different shape for the heads.